Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help ISU Actuary. This is problem number 6, the last one from the last exam MLC. Following this problem, I will be taking a break from exam MLC. Exam MLC ends this year, and effective fall 2018, it will be replaced by long-term actuarial models exam. So within the next month, hopefully or so, I will be creating a new channel for long-term actuarial models exam. I will also need to do the same for exam MFE channel. I will be creating investments in financial markets IFM exam channel soon instead. So I will be also winding down the MFE channel, and I will for a while post only problems for exams P and FM, which are not being changed until I create the new channels. But let's look at this problem. Part A, write down the Kolmogorov-forward differential equation for TQXJ, for decrement J, in the case of a general multiple decrement model. A person age 60 is subject to 3 decrements. You are given the following excerpt from a triple decrement table. So you have ages 60, 61 for 3 possible decrements with their probabilities. Decrement 1 occurs exactly 1/4 of the way through each year. Only 1/4 of the way. Only then. That's decrement 1. And its probability is 0.05 at age 60. Observed probability. TQX2, upper 2, is T times QX, upper 2, for integer x and t between 0 and 1. Of course, this is simply saying that there's uniform distribution of deaths for this decrement causing those deaths. That's decrement 2. And decrement 3 has a specific formula. It's 0. Probability of death from decrement 3, or departure from decrement 3, is 0 between t between 0 and 1/2. And then it's 2 times t minus 1/2 times QX upper 3, where QX upper 3 is the probability of decrement over the whole year. And this is only for t between 1 and 2, between 1/2 and 1. For part B, part 1, calculate 2p60 tau, so probability of survival from all decrements over 2 years. For a 60-year-old, and then the same over 0.8 years for a 60-year-old. C, sketch the graph of TP60 tau as a function of t for t between 0 and 1. Clearly label the axis and show all key values. And then part D, using the result in part A or otherwise, calculate mu, the force of mortality due to cause 2 at age 60.8, and then the same for cause 3. The multiple decrement model expressed as multiple states model has states 0, alive, 1 removed by decrement 1, 2 removed by decrement 2, etc. The general form of the Kolmogorov-forward equation is that the derivative And here's the solution. For part A, the multiple decrement model expressed as multiple states model has states 0, alive, 1 removed by decrement 1, 2 removed by decrement 2, and so on. The general form of the Kolmogorov-Forward equation is the derivative with respect to t of tpx, a matrix of transition probabilities, is equal to that matrix times the matrix of intensities of transition. And there you have the same thing written in the matrix form. And remember that the lambda upper 1 in this is obtained by adding the other entries in the same row. So the sum in each row in this second matrix is 0. So now if you want to write this derivative for entry in a row I and column j of the matrix on the left-hand side, then you can calculate it from this expression that this becomes either the sum over k not equal to j of tp x ik lambda kj of x plus t minus tp x ij lambda jk of x plus t, or the second form where the forces of transition are added up to give you this lambda j. The probability tqxj is written in the form tpx 0j in the multiple states model. Transition from state 0, alive, to j being taken out of the group by decrement j. So we just write this now with the same notation in the equation that we talked about. But in the multiple decrement model, the force of transition from j to k is 0 for all k, which basically says you can't go back. And lambda kj is 0 for k not equal to 0, because you can't move around from various decrements one to another. So that we obtain d over dt, the derivative with respect to t of p0j, equal to tpx00 times lambda 0j of x plus t, or in the multiple decrements model notation, this says d over dt tqx upper j is equal to tpx upper j times mu x plus t upper j. Well, this is basically saying the left-hand side is the derivative of the CDF, at least for a certain time interval of length t, is equal to the right-hand side, which is the PDF, the probability density function. The derivative of the cumulative distribution function is equal to the probability density function. For part B, we note that px tau is equal to 1 minus qx tau, which is 1 minus the sum of observed q's for all decrements, so that for p60, that becomes 1 minus 0.05 plus 0.10 plus 0.08, so ends up being 0.77 for 61.74. We just take these numbers from the table given in the problem. And 2p60 tau is p60 tau times p61 tau, and that ends up being 0.5698. For the second part, we have tpx tau, again equal to 1 minus these probabilities, so that the probability sought is equal to 1 minus these q probabilities for the time interval 0.8. Then we note that 0.8 q61 is 0.05, with the decrement actually occurring at time t equal to 0.25, and 0.8 q62 2 is equal, under UDD, Uniform Distribution of Death Assumption, 0.8 times 0.10, so it's 0.08. And then 0.8 Q63 will have a specific formula. That's 2 times 0.8 minus 0.5 times 0.08, and that's 0.048. Then we use all of these to plug in, and we get 0.8 P60 tau to be 0.822. The graph of TPX tau is of this form, and we see that jump from the fact that there is one decrement that operates effectively only at that time. For part D, from part A we have d over dt t qx upper 2 is tpx tau times mu x plus t upper 2. For this model, because of UDD assumption, we have for the second decrement the derivative of tqx is just qx upper 2. This gives us that mu x plus t upper 2 is equal to qx2 over tpx tau. In particular, mu at 60.8 is q60 upper 2 over 0.8 p60 tau, and we have these numbers, so we just plug them in, and this is equal to 0.121655. Similarly, d over dt of tqx3 upper 3, third decrement, that's tpx tau times mu 3, and the derivative of tqx3 is equal to 0 for t between 0 and 0.5, and then the derivative of the formula we were given, which ends up being 2 times q3 for t between 0.5 and 1. Well, this implies that mu 3 is 2qx3 over tpx tau. In particular, mu at 60.8 is 2qx63 over 0.8 p60 tau, and we have those numbers. We plug them in, and we get ratio to be 0.194647. Please remember, this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.